So we're back. So last time we graphed the basic functions, sine, cosine, and then we manipulated them by changing the amplitude, adding a phase shift. What else did we do? A y shift, a height shift. We changed the period. Now we're going to move on to the rest of the trig functions because those need to be plotted as well, of course. So let's see, we want a nice grid perhaps. If we want to do tangent, we're not doing theta anymore. Tangent of x as a plot with respect to y. Okay, we can of course always do it by plotting a few points that we know for sure. If they say to graph this on a test, and you can't picture it in your head, which I honestly can't even picture it right now, you can always just plot it. You can always just graph it point by point. So when it's 0, what is it going to be? When it's pi, what is it going to be? When it's pi over 2, and when it's pi over 4, what's it going to be? That's not in numerical order, but see, pi over 4, pi over 2. We'll do it in order for good measure. So tangent of 0 is going to be sine of 0 over cosine of 0, not theta, which is, if we draw a quick little circle, right? Here's 0. The coordinate is 1, 0. So it's going to be 0 over 1. Tangent of 0 is 0. Then pi over 4. Tangent of pi over 4 is 1. Pi over 2. This is an interesting one. What's tangent of pi over 2? Well, it's sine of pi over 2 over cosine of pi over 2, which is, up here we have 0, 1. So that means what we're looking at is 1 over 0. Don't freak out. That means there is nothing there. No solution. None. NA. Whole. Those are all acceptable ways of stating that. Alright? And then at pi, I'll come back to the graph, but I need to do work down here. Tangent of pi equals sine of pi over cosine of pi, which equals, if I look at my unit circle, pi is over here at negative 1, 0. That means it's 0 over negative 1. So it's once again 0 there. I'll just plot a few more things just to give us some more information to plot. Pi over 6. Interesting. Tangent of pi over 6 is sine of pi over 6 over cosine of pi over 6, which is this point on the graph at 30 degrees, which we know by now is root 3 over 2, 1/2. So 1/2 over root 3 over 2. What's my tangent? Well, it's this, which is this, 1 over root 3. So I'll write that. And I'll probably plug this into the calculator to find this value so I can plot it a little more nicely. And then let's say we do something sort of a little bit further, or we can plot it with that. That should be fine. Okay, so here's our information. This is helpful. It looks like at pi over 4, it's going to hit 1, so I'll just draw the 1 up here. Then know that this is 0.5. Don't be scared and think, oh, well, that's 1 unit. It has to be 1. Well, you can label the axes however you want, unless otherwise stated by a professor or otherwise, as I say. And then, let's see. At 0, it's 0. At pi over 4, it's 1. At pi over 2, it's no solution, / it's a hole in the graph, / we put this dotted line usually when we claim that there's a hole in the trig function. At pi, so pi over 4, pi over 2, next, let's see, that means pi would be here, right? And this would be pi over 4, 2 pi over 3, pi over 4 here. Alright, we randomly chose pi, so let's say, okay, when x is pi, y is 0. That works for me. I predict that perhaps since it's 0 here and it's 0 here, this may be where the tangent plot repeats, but that's not necessarily true. Let's see what happens. Pi over 6, it comes before pi over 4, and it's going to be a little bit non-uniform here, but I just want to use the x values that are easy to determine because we're so used to working with pi over 6. Again, you could use a calculator and just go down the line. Maybe I should pull the calculator out. I'll do the calculator on the next graph. But this will just be this is the way to do it with your brain and the unit circle and no calculator. So where was I? Pi over 6 gives me 1 over root 3, which is 0.577 something, which is like right 0.5678991, so 0.57, almost 0.6-ish. Okay, so it's not too scary. Once you start plotting it, you see, okay, dot, point, and a point here, okay, and I can start plotting this. Just remember that these trig functions are usually wave-like, right, because of their periodic behavior. So if you're doing a hand sketch like this, it's not going to be, your plot is not going to be this straight line because it's not linear. It's actually doing something like this, right? Which I didn't emphasize it enough, but I happen to know it goes like this, but I'm not going to spoil it. So my points could be a little bit better, I suppose. Okay, so what we really want to see is this. Make sure we say, okay, the pi over 6 is actually here on the plot. It might be easier just to show a tangent plot on the screen, but I don't know. In my trig class we had to draw it. I don't know if you will have to in yours. So at pi it's 0. And let's see what it is at 3 pi over 4, okay? Tangent of 3 pi over 4 equals sine of 3 pi over 4 over cos of 3 pi over 4. And on the unit circle, that's what? 1 pi over 4, 2 pi over 4, 3 pi over 4. So we know this is negative plus, and then it's a 45 reference angle. So it's root 2 over 2 comma root 2 over 2. The negative is there. So it's going to result in negative root 2 over 2 over root 2 over 2, which is negative 1. Okay, that helps us. So if the y value that comes out when you put 3 pi over 4 in as the x value, that means is negative 1, that means we do negative 1, oops, not at pi, put a point right there, alright? So this is just simply by almost guess and check, but just pick points and plot, a very old school strategy. Putting in 1,000 points into Python would be more modern, but this is just the way the cavemen did it, right? So if I continue plotting these, if I continue picking points in between here, I know what's going to happen. It's going to do this, and I'll erase this so I can draw it. It's going to come like this, an asymptote. Asymptote meaning the graph continually moves toward this dotted line here forever, all the way to infinity, all the way to down here into negative infinity. It continues to move down there, or I should say, it continues to move closer and closer to the dotted line without ever reaching it. Asymptote, right? That's what's happening right there. So it's going to do that same thing when it goes up here to positive infinity. Down here is negative infinity, right? As y goes down here to negative infinity, and as y increases up here to positive infinity, you're going to continually get x values that are closer and closer to pi over 2 without ever, x will never be pi over 2, right? But x will, the formal way of writing it is as y approaches positive infinity, comma, x approaches pi over 2, right? That's the formal way, because you don't really say, you don't put an equal sign between a variable and infinity. You just say, as our y goes this way, x continues to go toward pi over 2, but neither of these ever happen. You don't get to infinity, and a y doesn't exist for the x value pi over 2. Yeah, great. And so we have the asymptote at pi over 2. So from 0 to pi over 2, this is the behavior. Then from pi over 2 to pi, this is the behavior. And then it repeats doing this at another, let's see, doing this again, right? And it happens here again. So it happens at pi over 2, pi, 3 pi over 2, and then at 2 pi, we should expect it to cross again. Because that way, right? My scale's getting a little sloppy now, but should do that again. Right? This direction, this direction. That's how you would graph tangent if you really had no hints or tools or anything. You would just do this, say what is it at each of these points. The more points you add, the cleaner it's going to look, the more correct and accurate your graph is going to be. And so I want to do another one. Next we'll do cosecant, and this will be the slightly less caveman version of how to graph it, which will be just finding those points by asking the calculator what they are. And then next I'll do the even less caveman version, which is have the calculator plot it for you. But we'll just go up one step at a time just to practice these things and show you how to do each of these, work with each of these things. So let's say we want to plot cosecant now. Okay, I'm going to do the same thing as I did with tangent. Make a table of points. So when x is this, y is this, and I'm just going to go for it. So when x is here at negative pi over 2, when x is here at negative pi, when x is here at negative 3 pi over 2, and then we have to do pi over 2, pi over 2, pi, 3 pi over 2, 2 pi, alright. And I'm going to simply ask my calculator, what are those y values? First step is to make sure we are in radians, of course. We are now in radians. And I'm going to say, okay, can you please tell me, there's no cosecant on here, but remember that cosecant is 1 over sine. So I'm going to say, can you please tell me what 1 over sine of minus, make sure this is how you say negative and this is how you say you want to do subtraction. So make sure if you have a negative number going in, you push this, not this. Sine of negative pi over 2. Cosecant of negative pi over 2 is 1, okay? Good, we'll say this is 1 then. Okay, and then what is it for pi? Alright, it looks like if you do that, you're gonna get some divide by 0, not allowed to do in math thing. So we'll put a hole, no solution. Negative 3 pi over 2. I think I can do this. Bring it down. Go in here and just insert a 3, right? Whoops. Go up here, bring it down. Go right here and insert a 3. Alright, what do you got for me? 1 again, very interesting. So it looks like the points that I've chosen might not give me all the information I need. Just a hint right there that, I mean, how do I graph this? Doesn't tell me anything. But we'll try it with positive pi over 2. So I'll bring this down and then I'll delete the little negative on there. 1 again. So now you're starting to see a pattern, right? Not enough information. So let's go to the unit circle. We need a point between pi over 2 and 0, in my opinion. So I'll add pi over 4, see what it is. 4. Ooh, interesting. 1.414, which I'm pretty sure is the square root of 2. But then we'll say, okay, at pi over 4, which is halfway between pi over 2 and 0, right here, it looks like our value is going to be 1.414. So here's 1.5. We'll just estimate 1.414 to be right there. Cool. So what is this plot going to do? Let's see, I'll do it again with this, which is pi over 4, 2 pi over 3 pi over 4. This is 3 pi over 4. Let's see what we get. 3 pi over 4. Insert 3, okay, square root of 2 as well. Quite an interesting plot we got going on here. So like I said, it's going to have wave-ish behavior. So you're not going to want to draw this as the plot. To get a little bit more information, I'm going to just plug 0 in there, okay? Because I have a suspicion about 0, but we'll do 1 divided by sine of 0. Interesting. So I could have known in my head, actually, sine of 0 is 0. So 1 over sine of 0 is 1 over 0, which we cannot have, right? The way we usually do this is then we'll say, okay, this right here, the origin itself is a hole in the graph or an asymptote. Again, meaning there is no y value for that x. So if x is 0, there is no y value. The graph doesn't cross here. So, periodic behavior. At negative pi, we have an asymptote. At 0, we have an asymptote. Spoilers, at pi, we also have an asymptote. At 2 pi, asymptote. You don't need a calculator to know this. Sine of pi is 0, right? Because if you're here on the unit circle, you're at a height of 0, so sine of pi is 0. Sine of 2 pi is 0. Sine of pi is 0. So every time sine is 0, cosecant is nothing. No answer. So that occurs here at pi, 2 pi, 3 pi. Every integer increment of pi is a way to say that. You're going to have these asymptotes. And next thing is, okay, so as I said, we have periodic behavior. And remember that you're going to want to plot these like a wave. And so, again, without doing any spoilers, real quick, we can just pick some point in here that's somewhat interesting. So I'll just do pi over 8. I don't know why. Again, that's not one of our normal values that we use for an x, but we're going to use it because we need a value that goes here. Okay, 2.613, which is way up here. 2, 2.5, 2.6 is all the way up here. Gotta keep moving my y just to make this point. 2.6 is all the way up here. So we take, what, pi over 8 somewhere in here. 2.6 is somewhere up here. 2.613. Alright, and it's a little closer too, actually. I want to make sure this is a little bit cleaner. Okay. When you have this discontinuity, this dotted line here, you're going to have the same thing we had on the tangent function, which is asymptotic behavior of the graph. The line is going to be super close there to that asymptote. Then it's going to slowly come away, and it's going to come here, and it's going to be a wave shape. So remember, we're not doing this. We're doing this. Wave shape. Then it goes back up. Then it goes up here to this dotted line, and asymptotic behavior once again. So remember, here, the graph does not touch 0. Does not touch x equals 0. Here, the graph does not touch x equals pi. The graph continues to get closer to this line and does that all the way up to infinity, never reaching it. Sounds bizarre, but another tip I can give you is when something sounds bizarre and non-intuitive, like discontinuities in a graph or a function, or infinity in general, you know, or eventually you'll try to grasp quantum mechanics perhaps, it makes life a lot easier to just say to yourself, the graph continues to approach pi infinitely, and I accept that. It's not scary, right? It might sound trivial, but that attitude will save you a lot of grief. Because, I mean, I know I myself am very inquisitive, and I want to know, well, why? What's the actual answer there? You know, when there's something like an infinity or a hole in the graph, it sounds wrong, and you want to perhaps come up with your theorem that's going to explain it better than that because it sounds wrong. And that is the thing that you should do. Once you've gone to school and accepted it for all those years, you can go back and start to question the types of things like this. But if you question it in the middle of doing it, it's only going to hurt you because your mind's going to get twisted in a knot. It just helps if you say, actually, there's nothing weird about the graph going to infinity, continuing to approach that asymptote without ever touching it. That is a thing that can happen in my world. You accept it and you say that it is there and it's fine. So anyway, that's what's occurring here. Again, the formal way to say it here is from the left. The formal way to say it is as x approaches or goes to or tends toward 0 from the right. This means from the right. As we come here from the right, doing this, as the graph comes to 0 from the right, what happens is, and that's implied here, I'm not going to write it, but it means what happens to y is that y goes, you can see, what does the graph do? As x goes this way toward this dotted line, y goes up to positive infinity. And as x goes to pi from the left, I'm not going to write from the left, you know what that means now? Y goes to positive infinity as well. You can see it happening here. X equals pi. From the left, graph goes to infinity. Sometimes I'll say graph or y value interchangeably because y is a function of x here. So y is being changed by x. When x changes, y changes. And I have to plug in 2 points just to be super sure, in my opinion. So negative pi over 4 is negative square root of 2. Negative 3 pi over 4 is negative square root of 2 over 2, aka negative 0.707, which is getting interesting because then that means down here we have, what is this? I did 1 and 2, negative 1, negative 2, which means that negative pi over 4, we get this negative 1.4-ish thing. Alright, I'll put a point there. And then as the graph continues over here, 0.707 is going to be somewhere around here. So, okay. Where did I get negative pi over 2? Come on, man. Oh wait, that's sine. That's why. I did not do 1 over that. That's my mistake. So, on this side we get that, and I should do 1 over sine of negative pi over 2 is negative 1. So, that looks kind of interesting, right? So it's this mirror down here of these 3 points appear down here when it's going negative. And spoilers, I'll just tell you the rest of the points because it is a lot to plot. The plot does this, right? And so the periodic behavior of cosecant is that it repeats in this manner. Sort of a funny looking graph, I would say. But, like I said, we take what we get, and that is it. So that's cosecant for you. Continues to do that for all eternity. If you look for any of these y values in here, you're not going to find them. There are no y values of cosecant in this regime between 0 and 1. So now that we've done the semi-less caveman way, what did I do? Sine, cosine, tangent, cosecant. Let's just do secant by using the calculator to our full advantage, right? So if we want to plot this, I'm not even going to label any of the axes. I'm going to just go right into my calculator. And since I know this, 1 over cosine is the same as secant, we'll go into here and say y equals 1 over cosine. Oh, is it updating live? 1 over cosine of, and then we have an X button right here. It is what? We'll say okay, and then graph. There you are. The secant plot looks similar to cosecant, right? Except if you look right here, which I believe you can see my cursor. It does this. This is 1. It does this, and then the asymptote where it goes up to infinity and then poof comes down here from negative infinity is even, just how cosine is even. See how it mirrors over the y-axis? Whereas our cosecant would do this periodic flipping over the x-axis behavior, but it's an odd function because it's 1 over sine. It does not mirror over the y-axis here. It actually flips down to negative, then up to positive, so negative, positive, negative, positive. And this secant is even because it's over 1 over the even function cosine. So, again, this is really loose sketch here, but this would go down to this point. Let me move it a little. This is -1. This is +1. Right? This whole area, there are no solutions to secant. And so far we have graphed 3 varying levels of making it difficult for ourselves to graph, like I said. 3 different trig functions being graphed. So there's only one left to do. And why not do it the least caveman-y way possible and have Python do it for us? Okay. So what we've done here is first we're going to say x gets some set of points. That's what np.linespace does. X gets some set of values between -2 pi. That's what np.pi is. And +2 pi. And then it's going to make 1,000 of those points. Here we're going to say, okay, our cotangent of x is just 1 over tangent. This is a numpy function, tangent. So it's just calling upon the function tangent here. Not sure if there's a cotangent one. Could be, but, do it this way, it's fine. And this is just to make sure that when we run into the points that don't exist on the plot, and we divide by 0, that it simply changes those points to NaN, not a number. So it's just saying that once you get, at any point, if you get a value that you see here is so small that it's on an order less than 10 to the -8, we're just going to call all those not a number, rather than trying to let the program calculate at that point 1 over 0. And the absolute value part here, this np.abs, is saying for either positive or negative cases, it's fine. And then plt.figure. This plt is matplotlib.pyplot. plt.figure, we're just going to say this is a figure size. It's just generally used. This is what's going to do the plotting. So first argument of the plot function is our x value. The next argument is our y value, which is cotangent of x, which we made right here. Then it's named cotangent. And this is just to customize the axes so that if you don't do this part, it'll still plot it. The plot will look exactly the same, except for the fact that it might arbitrarily choose 1, 2, 3, 4, 5, which in Trig, a lot of this stuff happens. It looks nicer if you plot it at pi over 2 pi, 3 pi over 2. So it's going to do pi ticks here is, again, creating another set of points, which instead of using line space, now we've used np.arrange, which is just saying it's going to make well-spaced values between -2 pi and +2.5 pi and positive pi over 2. So it'll make all the ticks in between line up equally spaced to make sense with the values -2 pi and pi over 2. And then this is just labeling them You don't have to worry about a lot of this, but and then x ticks is setting those ticks to be that, right? Setting what the values of the tick is and what the labels on the tick are. This whole thing, I mean, this whole part is really not necessary. We can plot it without it and see what happens. And then this is just xlim. Plot.xlim does the sides of where the graphing is going to stop happening, and the top and bottom are the y, the minimum and maximum y. Here's the minimum and maximum x, and labels the x-axis as x, labels the y-axis as cotangent. Title plot of cotangent, right? And so we'll run it, and when we run it, we get this beautiful thing. There it is. This is what cotangent looks like. Here you can see pi over 2, pi, 3 pi over 2, 2 pi. It appears that there's an asymptote at 0, an asymptote at negative pi. So the period of this function looks like it's pi, which makes sense because that's what the period of tangent is, and this is 1 over tangent. And I'll do it again without all this because this is something that's a little bit of work, but we'll run it without that and show you that. See here, same plot, but now it's these kind of unfitting 0, 2, 4, 6. That is just how matplotlib default makes the x-axes. This isn't a Python video, so we're not going to go into all that. But you can see, you know where pi is because it's here at 3.14. So 3 would be halfway between 2 and 4. It's a little tiny bit to the right of that, so this makes sense that it's asymptoting at pi. And then the next asymptote should be at 2 pi, which is 6.28. And there you go. There it is. So that is, again, just the way to do it as the furthest from being a caveman. And I mean, I can also note this out and show you what will happen if you don't worry about the asymptotes in the program. Remember, a computer, the way that we differ from computers, remember that I said just accept that the y goes to infinity and the points will continue to approach that asymptote from the left to the right. And just accept that and it'll make life easier. Well, that's where we're separate from the machines. The machines cannot do that. The machines have a very hard time of accepting that, and that's why if you don't code in something that handles dividing by 0, they just say, oh, well then, it looks to me like the point here down at negative infinity, that they aren't going to call it negative infinity because the robot doesn't have because the machine doesn't have a concept of infinity. It'll say, oh, it looks to me like at infinity, the graph is here, and negative infinity, the graph is here. What's between those 2 points? Oh, well, it must be a line, and it just connects the 2 points, which is wrong. This is not a correct plot of cotangent. Interestingly, it didn't happen here, but that must have to do with 0. I think it knows that 0 over 0 is definitely wrong, whereas some number over 0 is not necessarily wrong. Anyway, so we have to put in the exception down. I'll take this note out. We have to put in the exception to say, hey, make sure you know that the graph is never here, right? So even with that exception, we haven't explained to the machine that the plot asymptotes there and goes infinitely because it doesn't even plot that many points. All it does is it just makes points smaller and smaller, and if they're smaller than 10 to the minus 8, which is 1 over 10 to the 8, or 1 over 1 with 8 zeros, if it just is being told, if you've come across a value that small, don't worry. As you keep going and making numbers smaller and smaller and smaller, past that, just put in nan, and what nan does is it's a blank. It leaves it empty. It'll make an empty value there. It'll be a garbage value. It'll say nothing is there, right? Whereas if hypothetically, if I add more points by changing linspace here, this 1000, if I add more points to the plot, then it would continue. It would make and I extended the y-axis, right? If I extended that, if I extend this y-lim, Right here, I can do 100 to 100, see what happens. Negative 100 to 100, I should say. You'll see that as it asymptotes, there's more values here on the actual cotangent function, but we've told the program, the computer, don't plot this. Just say anything that small, 10 to the minus 8, just say nan. Leave it blank, right? Because we don't want to confuse the machine. So, like I said, this isn't a Python video. I just wanted to add the different ways that you can plot, and we will continue. Okay, and so of course we have some problems here. What is the y-intercept of y equals tangent of x? The y-intercept is this right here. Where does the graph cross y? When does it happen? Well, we just plotted it, so I happen to know that it does this stuff, right? Asymptote, and this stuff. But the rule for finding y-intercept is pretty basic logic. Whenever the x value, so we have 1, 2, 3, whenever that's 0, if x is 0, then you're on the y, right? So whenever the graph crosses y, whatever it does, it's happening when x is 0. So y equals tan of x equals, the way to write this is y of 0 equals tangent of 0. And this value is sine of 0 over cosine of 0. I go to my quick unit circle sketch here at 0 pi. The coordinate is 1 in the x, 0 in the up and down. Alright, so sine is 0, cosine is 1, 0 over 1 is 0. The y-intercept of tangent of x is 0. So what about secant of x? Y of 0 equals secant of 0, which equals 1 over cosine of 0, and cosine of 0 is 1, so it's 1 over 1, or 1. The answer is 1. Kind of easy hitters right there. So now we're back to what we did in the previous video, which is graph the function, but it's slightly manipulated in some way, like this a here is looking like 3. The absolute value of a is 3, so the amplitude is 3. So tangent of x, which crosses here, or comes out of this 0 to begin. So our tangent plot, we just did it. So I'm just gonna use that information that we found. Say here's what tangent does, then another negative pi over 2. There's an asymptote at negative pi. It crosses, so it goes cross, asymptote, cross, right? Negative infinity, infinity, asymptote, and it continues to do that. This amplitude of 3, right, what I've plotted here is y equals tangent of x. This amplitude of 3 will simply take this whole plot. Every value in there, in this function, it's going to sort of cause it to stretch vertically. So if this is the original right here, okay, then our 3 tan of x will just look a little bit more squished like this. Okay, that's all that's gonna happen there. It's even barely noticeable in my sketch. But I'm not gonna go draw this whole thing and try to make it accurate on here. Just know that here at pi over 4, normally tangent is 1, right? Both of these are root 2 over 2, which means it's 1. And when we have this function, 3 tangent of x, well, instead, it's just going to be at pi over 4, 3 times that 1, which is 3. So that's really all there is to that. So at negative pi over 4, I can also tell that it's going to be negative 3, whereas just on y equals tangent, it would be negative 1 and 1. Very minor difference. So the domain and range, well, the range is the y's, easy, negative infinity to infinity. parentheses, not brackets, because we never include infinity. And then, and the domain is also all real numbers, excluding this pi over 2, 3 pi over 2, 5 pi over 2. So another way to write that is x doesn't equal, and you can use some letter to represent integers like k or n. So I don't know how technical I want to get. Don't worry about this, but technically, I mean, this is saying odd numbers in front of pi over 2 are not allowed. This is not within the scope of what we're doing, but it's technically x includes, or yeah, see, this is too much, but x includes all real numbers, which is what this says, you know, except odd numbers in front of pi over 2 here. But we're not going to dig that deep. So let's see, cotangent, except the period is altered. So b is pi over 4, period is 2 pi over b, absolute value. So t is 2 pi over 4, which, you know, I always like to write 2 pi and 4 over pi. We flip it, multiply, which means 8 pi over pi, which means 8. So it's going to have a period of 8. So all we have to think about is what was our cotangent plot. I don't want to go back, but I'll just say, you know, 1 tangent x graph. So this is just going to be quick sketch is what this is called. The quick sketch method. This is an asymptote, the origin. All right. And a period of 8 rather than its original period, which was pi. So, right, a period of 8 instead of y equals cotangent having a period of pi. Our function, which is cotangent of pi over 4 times x, has a period of 8. So if this is one full period, which would normally be pi, we're just going to say, all right, it's 8. All right, so from dotted line to dotted line is 8. Then the next one is going to be 16. This one over here, this is 0, will be negative 8. That's probably the quickest sketch you can do of cotangent of pi over 4x. Domain and range. The domain, again, not going to do that technical thing, but the domain is all reals, or negative infinity to positive infinity. X cannot be 8, 16, 24, right? Same goes for negative 8, negative 16, negative 24. There's no x's like that. And the range of this is everything, right? We'll go up here to infinity, go down here to infinity. You're going to get every y value imaginable from that function. Okay? So, secant, again, was... Let me get the calculator. Right, so... Okay. So to make life easier, we're going to use a calculator on this one. Saying, okay, and here we want secant, which is 1 over cosine. Let's graph it. Alright. We know that it looks like that. So to begin my sketch, I'll say here at 1 and here at minus 1. We would normally, just graphing that, have the symmetry over the y-axis here, where the vertex of that part of the graph is 1, but it appears our amplitude is 3, which means that the solution to each thing I put at each x, the y that I get out is going to be multiplied by 3, plus it's negative, so it's going to be flipped and mirrored over the y-axis. So what I'm going to do is write 3 and negative 3, okay? And then here, where you have, which we're seeing on the calculator, right? Here where secant by itself begins up here at the positive 3 and goes up, I predict It's actually going to do this when I add that -3 in front, right? Do you see why it would do that? Let's test it. So I'm going to change this to, instead of 1 over cosine, it'll be 3 over cosine. Hopefully I'm not moving too fast by doing that, but it's right if you think about it. If 3 secant is 3 1 over cos, then it's this multiplying out makes it this. Yeah? Okay, and then I add the negative. Let me insert a minus sign. Plot that. Should be, whoops, and plot that. It should be secant, except right here, right? The minus sign has flipped this whole concept of secant over the x-axis. So if this is your x-axis here, when you have a function that is multiplied by a minus sign or times -1, it's going to flip over the x-axis. So we're going to go asymptote, asymptote. Thing happens here at 3. Asymptote. Thing happens here at -3. Right? You seeing why I'm doing that? Then we have pi over 2 being multiplied by x here in the argument. And so remember what that is going to do is period is 2 pi over absolute value of b. Our b is pi over 2. So period is 2 pi over 2, same as flipping and multiplying, which means the period is now pi, which means the period of our function here is pi. So if the graph begins right here, going east and west, right? The graph begins here and goes down to infinity, comes up from negative infinity, I should say, comes down from positive infinity, then goes back up to positive infinity, and comes up from negative infinity to here. That's considered one period, right? Because we're back at this same point. Now, what happens next is another cycle down. Then, you know, if we were, does it let me go this way? Sure. Down there, down from here, up, right? It's going to do that again, and up. That would be a second period. So one period is this distance, and we're just going to annotate that distance as pi. Technically true. I'm not following these directions exactly, but the point is to understand how to draw the graph and how to know the difference between the original secant and this altered secant. So we did it. That's 1 pi there. And I can even put it in the calculator, although I don't think it'll make a difference. Yeah, it'll just look a bit. Yeah, the axes are not labeled, so it won't actually make a difference. This will change, but okay. And I'll just do one more. What's this? And I'll try to do this one sort of quickly. So I want my original cosecant, which is 1 over sine. Okay, it looks like this, I believe. Yep. And here, and here, and here. Okay, with the dots, and then this is also an asymptote, and the dots. This is my x, this is my y. I apologize, actually. See this negative? Gotta pay attention. Luckily, I have this cool tablet, so there's no problem at all. I'll just do this. Isn't that nice? How convenient is that? Okay, rewrite this y and x. Okay, getting a little sloppy. I'm sorry about that, but again, you can pull up any of these plots on Google or type in your calculator. So as you see on the calculator, we have original cosecant function plotted. The negative of that is flipping it over the x-axis. So instead of beginning with this positive parabola looking object, it begins with this negative one. And the only other thing is this pi. So if b is pi, period is 2 pi over b, period is 2. I can see here that the graph repeats right here because it goes, again, I'll do highlighter, it goes like this, then it goes like this, Then we're back to where we started. It goes like this, repeats. So 1 period is 2 integer value in length. That is 1 period, and that's all you gotta do. Domain and range. The domain is going to be any x except right, any x except 1, 2, 3, -1. There's more mathematically correct ways to write that, but this isn't that class. So in the range, considering the graph goes up to infinity here, and up to infinity here, and down to infinity here, and down to infinity here, the range is negative infinity to positive infinity. Alright? And that's going to do it for tangent, cotangent, secant, and cosecant, how to plot them, and I'll see you in the next video.